Okay, so a 2 by 2 determinant is pretty straightforward to solve. We multiply this, subtract these two multiplied, and set it equal to 0. So we'll get alpha minus e times alpha minus e, so alpha minus e squared, minus beta squared is equal to 0. And this is pretty straightforward. So we can say alpha minus e squared is equal to beta squared, or alpha minus e equals beta, well, plus or minus beta, because we're taking a square root. So the energy is equal to alpha plus or minus beta. So if we plot this sort of on an energy axis, we're going to have, we put two atomic orbitals in, we get two molecular orbitals out. So we'll kind of reference this relative to alpha, right? This is the orbitals kind of by itself, right? This is just a 2p orbital by itself, not mixed with anything. And so we have one energy level, E plus beta. If we remember, beta is negative. So if we add beta, it's lower in energy, because that's confusing. Sorry, and that's not E plus beta, that's E equals alpha plus beta. And we have E equals alpha minus beta up here. Now we have two electrons. We have one electron in each of these p orbitals. And so our two electrons go down into this lower energy. So the total energy of the electrons is less than the energy of the electrons in their separate orbitals. And so our total electron energy is 2 alpha plus 2 beta. So this is our total energy of the electrons. And this is a stabilization of 2 beta relative to the electrons not interacting with each other. Right, or about 150 kilojoules per mole, according to the value of beta that we assumed before. Okay, so this gives us a picture of sort of what's going on in terms of the energies. One thing to note is that these assumptions that we are working with don't work for all molecules, right? So this only works for conjugated pi systems in organic molecules. So this is, a pretty limited scope, but, this is a set of useful molecules. Molecule has to be planar. All right. And basically it mostly works the best with hydrocarbons. You can introduce heteroatoms in like nitrogens and oxygens, but you have to account for them, right? Your alpha and beta assumptions don't work out so well because you now have things that are not carbon that are present. So then the next question is, what do the wave functions look like? So what we need to know is what are C1 and C2. And so we can go through this mathematically. Since we know, the alpha and beta values, what the energies are, we can solve this. But we'll just go to the solutions in this case. You can look in my lecture notes or in the book for going through the actual solution. But I think what's more interesting is to see what these look like. And essentially, we get that C1 and C2 are equal to each other. And we can have the case where they add together and the case where they subtract. So our case where the energy is alpha plus beta, we get our two 2p orbitals add together, and we form a pi orbital, a pi bonding orbital. So right, this would, if in diatomic speak, this would be a pi u orbital, but that we basically only use that for diatomic molecules. And then we also have our higher energy orbital is an anti-bonding orbital. We end up with sort of similar shape that we've seen before, where we have a node between our two carbon atoms. Right, so this is a pi anti-bonding. Okay, and so this is a way that helps us see, what's happening with the pi electrons in this system.